So I mean, it's obviously possible to make computational errors with doing EROs. When it comes to the test, what you need to know about that is that I tend not to penalize people too harshly for what I would consider like silly mistakes. If you make a silly mistake, let's say you make a sign error or something, and then you carry it through, if you draw the right conclusion based on what you get for a row echelon form, even if it's the wrong answer to the problem, if it's the right conclusion based on the steps that you did, then I'm not going to penalize you for that. In fact, I will probably take off very little credit. I might take off a small amount just for the error in the solution method. But that's actually a better result than somebody who is basically doing everything correctly, but then draws the wrong conclusions about the theory. That's what's more important to me is, do you know like what the pivots tell you about these three possibilities? That's really what I want to see you guys being able to do. So, yeah. So in other words, don't get hung up too much. Don't spend forever on ERs. It's okay to check your work and just make sure maybe something doesn't feel right to you. The numbers are too ugly. You know, Dr. Hammond wouldn't ask us to do a problem where we've got double-digit fractions and horrible things like that, right? So, yeah, that's true. But on the other hand, if you've done the theoretical things right, I would rather have you finish the test. You know, not spend all your time trying to fix something that's really just a silly mistake. I'd rather have you finish the test than to like get distracted by something that's kind of just tedious. Does that make sense? I'm just giving you a strategy for the test, so that hopefully you'll do a little bit better because of that. Okay, let's do a couple more examples then on the matrix stuff, and then we'll go back and talk about chapter 1. Okay, so number 4. Let's assume that A and B are 4 by 4 with the determinant of A equal to 2 and the determinant of B equal to 3. So let's find the determinant of the matrix A inverse times B transpose times 2B inverse. Okay. This hopefully looks familiar from the group work that we did last week. It's kind of an example similar to that. I didn't give you a specific choice of matrices A and B. I just said they're 4 by 4. Didn't tell you anything else about them. So I'm really testing you more on your knowledge of the abstract properties of determinants, right? Which we listed in class last week. So basically you want to try and break this thing down, right? And so let's just, maybe we'll review a couple of things just really quick before we get into it. How does the transpose affect the determinant? Leaves it the same, right? Okay. How about the inverse of a matrix? We take the A inverse. How does that affect the determinant? Right. The determinant of A inverse is 1 over the determinant of A. What about multiplication? You multiply two matrices together and take the determinant. How do you find the determinant of the product? Okay, I'm not asking in this particular case. I'm just, suppose I have two matrices. So let's just, I don't want to get confused with the example. If I just take two matrices and multiply them together, what's the method for calculating this determinant? That's what we're looking for. The determinant of the first one times the determinant of the second one. Right. Okay, so determinants respect multiplication. inverses create a reciprocal. Transpose does nothing, right? So maybe that's enough to get us at least started on this, and then we'll see what else we need to think about. So you see we have like a multiplication right here. In the middle, we have sort of this whole thing times this whole thing. So according to the property that we just wrote down, what we really can do here is find the determinant of the first one, which is A inverse B transpose, and multiply it by the determinant of the second one, which is 2B inverse. Okay? And you guys already told me that the transpose doesn't do anything to the determinant. And here's another product, kind of a product within the product. So I have another multiplication here. So I could think of that one as the determinant of A inverse times the determinant of B times the determinant of 2B inverse. Right? Okay, and then as you told me, just following the stuff you guys told me, the determinant of A inverse is just 1 over the determinant of A. And then we have the determinant of B, which I'll come back to in a minute. And then the determinant of 2B inverse would just be 1 over the determinant of 2B, right? So basically, that's breaking it down for us. Okay, so we have some of the numbers already. The determinant of A is 2, so it's just going to be 1 over 2. And then the determinant of B is 3. And then we have 1 over the determinant of 2B, which would that be 6? No. Remember this one? This is the tricky one. Right, I told you the matrices are 4 by 4. To get the matrix 2B from B requires you to multiply every single row by 2. And each time you multiply a row through by 2, the determinant goes up by a factor of 2. So actually, because there's 4 rows to B, you're going to take the determinant of B, which was 3, and it's going to get powered up by 2 to the 4th power, right? This is an important one to remember. It's not just times 2, it's times 2 to the 4th, right? Okay, great. So if you believe all of that, then you just have to multiply the numbers out, and you're going to get 1 over 32. Okay? So, just a reminder, practice those properties of determinants, because then you can answer questions like this really easily. There's some good examples of this on the group work that we did last week too, so you can take a look at that also. We good? Okay, let's do one more kind of more theoretical type of problem here. Okay, so suppose, this one's going to feel a little weird, but that's all right. Suppose A and B are invertible n by n matrices. So notice I said invertible, right? So we have, they're both invertible, they're both the same size. Okay, so if, let's just imagine, again I'm not giving you specific matrices, but I'm just going to do this little symbolic expression. If A times B, let's imagine that it equals negative B times A. Just suppose that happens to be true, for whatever reason. Then here's what I want us to do. Explain why n must be even. That's a little bit weird, because what we're saying is that, okay, if AB is equal to negative BA, then the matrices A and B, they could be 3 by 3, they could be they could be 4 by 4, or 6 by 6, or 8 by 8, but they can't be 3 by 3, 5 by 5, or 7 by 7. And that seems so strange, in a way. So this is a kind of a theoretical question, and what I can tell you is I would never ask it to you unless I gave you a hint. Question?
Are they skew symmetric?
I didn't say that. Skew symmetric, that's not a bad thing to review because I don't really have it on the review sheet anyway here. So just remember, skew symmetric means that A transpose is equal to negative A.
What would that be 1 at that even?
although I could give you a question that I think it's probably on the sample midterm, where I say something like, yeah, a skew symmetric matrix. Well, let me come back, I'll come back to that point. But yeah, this is the definition of skew symmetric. So the hint here, that's not a bad thought. That's actually a really good thought. But see, we don't have any transposes here, so I don't really see the skew symmetry coming into it. So here's the hint. The hint is determinants. Okay. I don't know if that's very helpful or not. So what do we know? We know that A and B are invertible. In terms of determinants, what does that tell us? If I have an invertible matrix, what can you tell me about its determinant?
It's not zero.
Correct, it's not zero. So A and B, both of them, have a non-zero determinant. That's certainly true. Okay. And then the other thing, and this is obviously important, is that we're assuming that AB is equal to negative BA. By the way, this is a great opportunity for me to remind you again that matrix multiplication is not commutative. A times B does not always equal B times A. It might, but it doesn't have to. And here's an example where it doesn't. I'm assuming that A times B does not equal B times A. Instead, it equals negative of B times A. Okay. So, that equation in the box, together with the hint, is there something we could do?
What are you talking about? Which two matrices inverses of each other?
No reason to believe that that's true. Just
I don't know if it'll help, but I think of it as equal determinant of A times determinant of B. The only reason that the determinant of negative B times A is that you permute it a number of times to turn negative. But that's just a thought. I don't know.
Yeah, that's helpful. So you're kind of looking at the determinants with respect to these
Yeah.
equations, right?
Yeah.
Here's the key thing, guys, and then your thought process is right, and it's going to come up when we go a little further into this. If two matrices are equal, then their determinants are also equal. If I have two matrices, so if x equals y, and those are matrices, then the determinant of x, obviously, because it's the same matrix, is the same as the determinant of y. The number that you associate with x is the same as the number that you associate with y, if they're the same. So if I'm assuming that these are the same, then would you agree with me that I could say that this is equal to this? If I start by assuming this, then by taking determinants of both sides, it still has to be the same. Yeah? Anybody not happy with that? That's kind of a key step. Once you do that, okay, so now you have determinant of AB. What's your automatic reflex to do with this? Exactly. So the determinant of A times the determinant of B shows up right here, right? Okay. And how about on the right-hand side? How does that split up? Determinant of negative B times the determinant of A, right? All right. This is looking really good. Let me give myself a little more room over here. You guys take a look at that, see what you think we might do next, and then we'll see. The thing with these theoretical-like problems is they actually don't take very much writing to get them to work out. So, all right. Based on what you see there, what might you suggest we do?
Multiply both sides of the determinant of B.
Yep, I could multiply both sides by the determinant of A inverse. That's kind of equivalent to doing what? Dividing by?
The determinant of A or B.
Correct. So I could divide both sides by the determinant of A. Is that a safe thing to do? The only thing we can't, well, but we're dividing by a number, right? Not a matrix. Determinant is a number. So yeah, I would not want to see somebody try to divide. So this would be terrible, right? If you started from here and you did something like this, right? Oh my gosh. I would get out my red pen and right, you don't want to divide by a matrix, but dividing by a number is okay. There is one specific number that we should not divide by. Which number is that? 0. So is the determinant of A a safe number to divide by here? Why? Right, A is invertible, so therefore it has a non-zero determinant. Let me write that down. So since A is invertible, that's from the invertible matrix theorem, right? The determinant of an invertible matrix is not 0. So thus the determinant of B is equal to the determinant of negative B. So we basically cancel. So we let me just add in here. By dividing by the determinant of A, we get the determinant of B equals the determinant of negative B. Right? I'm still trying to explain why n is even. So far I don't even see the n anywhere. But we're getting close. We're getting very close here. What can I do with this?
Can you just be B equals negative B today?
Say again?
Can you just turn back into the matrix, say B is equal to negative B or no?
I don't know if B is equal to negative B. That would be the only. That would just be if B was like the all zero matrix. Then that would be true. Any idea here? Don't even need to go that detailed. Yeah, we can make it even simpler than that. Let me suppose it was something different. Instead of a minus, by the way, that minus sign is really like a scalar times b. If it had been determinant of 2b, if it had been like a different number in front of it, would you have had an idea what to do with that? You would do what?
Multiply the b.
By 2? Is that right?
Oh.
Okay, see, we're back to this property again. Let's go back to the previous example. The determinant of 2b would have been 2 to the 4th, right? In this case, it would be the nth power, right? And it's not a 2, it's actually, in this case, it's actually a -1, right? Oh, so doesn't that tell us, I think that's going to do it. Because doesn't that tell us then that this is really the same as -1 to the n? That's just my scalar raised to the size of the matrix times the determinant of b. And now by the same exact reasoning, since the determinant of b is not 0, because b is also invertible, divide by it to get 1 is equal to -1 to the n. Basically, you're canceling the. So, yeah, you're basically just canceling the determinants, and you're just left with this. And of course, the only way that this could be true is if n is even. Squared power, 4th power, 6th power cannot be an odd power. Make sense? I mean, if I wanted to sort of streamline the solution for you really quick, let me just show you how I would, just to see the short version of it. Basically what you do, you start from here. You just break it down as the determinant of AB equals the determinant of -BA. Then you bust it apart. Determinant of A, determinant of B equals determinant of -B, determinant of A. And see, while you can't just cancel matrices, you can cancel numbers. And as soon as these are numbers, left and right doesn't even matter, right? So whereas the difference between AB and BA is important up here on the level of the matrices, once I've changed them into determinant values, which are numbers, now I don't care whether, if this is on the left side and this is on the right, doesn't matter, I cancel it, it's a number, right? Okay, and then I do the same thing here. The only problem is this -1 to the n has to be pulled out. So you're left with that equation. It's pretty cool. Okay. So you could go back to, we could go back to Brandon's idea real quick. If we had a skew symmetric matrix, we could imagine kind of doing the same thing we did here. In other words, taking the determinant of both sides. What's the determinant of A transpose equal to? Determinant of A, good. And on this side, of course, this is the determinant of negative A, so that -1 to the n would pull out, times the determinant of A, right? So you'd have, so you could play that game with this too. I think this is the one that's on the sample midterm, so I don't want to do the whole thing. But basically, you would get something that's like that. And then if A was invertible, you would cancel the determinant, just like we did in the example, and we say, oh, n has to be even. This is just nice. The thing I like about the problem is it forces you to remember the properties of determinants. It forces you to remember that invertible matrices have non-zero determinants, right? And shows you the beauty of using determinants to solve a problem. I kind of like it. You guys okay with it? Everybody hanging in there? It's tough to kind of be here like Sunday night. Like I'm going to see you again tomorrow night in the same place. But it's okay. Especially when it's kind of a cold, rainy day. You guys are the diehards. You show up on the weekend, pull yourselves out of your house and come out. That's great. Okay, I only have a couple more problems to go over, and they both have to do with chapter 1. So I've kind of done what I wanted to do as far as like the matrices, the solving systems, and I didn't do the Gauss-Jordan method. I don't promise in a review session I'm always going to do absolutely everything that there is to go over, but I'm giving you hopefully enough review on some of the stuff that you'll take it with you and kind of know what you need to look at. Jim?
I just have a general question. If like we have a matrix question, solving like a system of linear equations.
Yeah.
If it's anything but n by n matrix, we have to use Gaussian elimination, correct?
Right. The only time you can use Kramer's rule is if you have an n by n matrix that is invertible. Right. If your matrix is not invertible, it's not square, then the only way to solve the system really is to just do the Gaussian elimination.
And we
Figure out where your pivots are and go from there.
we would be able to use the adjoint method to find
Right.
the inverse.
Right. All that stuff. If the matrix is